Okay, so the next book that we're working on is this book here, Thinking with Types, and you can choose how much this one costs. You move it here, it costs 25 bucks. So it's cheaper than the other book, but this book is, I think it would be considered more advanced than Haskell programming from first principles, and there's some interesting stuff in here, which I think is cool. Let's see, we can read the table of contents. So we're gonna learn about, we're gonna learn a lot of terminology that I don't know. So isomorphisms, I know what an isomorphism is. Cardinality, I kind of know what it is. I read a good amount of this chapter already. Then we're gonna talk about lifting restrictions. So one of the things I'm interested in learning is this GADT idea, GADT. I don't know how people pronounce it. I've heard about existential types. I don't know if coercions are what I think they are, but there's all kinds of like really interesting stuff about types in this book, and I'm hoping that I can learn them. How long is this book? This book is a lot shorter than Haskell programming from first principles. So in theory, we can finish it faster, but it's also, again, more technical and in-depth. So it's 230 pages. So hopefully it won't take us 6 months to finish, but this is what we're working on. If you have any questions about the stuff we've already done, I put it in that GitHub link. Oh, let me make a command for that as well, because maybe that's useful. Custom commands, create. What do we want to call this one? Topics. Let's call it topics. So add topics to the stream on here. Paste, save, close. Okay, so if you want to there we go. So if you want to add information to the stream, like you're interested in learning something and you think that I would be interested in learning it, feel free to post it on here. So we've done, well, technically I didn't do the first book on here, but I've done the second one, and so that's the plan. So I should fix this as well, because I already forgot that it was plural. Is there a way? How do I? Okay. You can't just add like an alternative name to this. Save. Okay. Neat. All right. So let's call this. I think there are exercises in the chapter, and there are no exercises at the end. Let me verify that that's true. Yes, that's true for chapter 1. So we're just gonna call it. We're gonna make a stack project that's just called. You know what we should do? In here, I want to put the title of the chapter. I didn't do that before. The algebra behind types. And then we'll open this up and we'll get started. I think we lost a few folks that like quickly went over the channel and moved on, but that's fine. So first we're going to talk about isomorphisms and cardinalities. So I'm going to kind of read through the book. I have a physical copy here. So I'm going to kind of read through the book, and then we'll start talking about some definitions. So let me put some information in here. So data, void, data, data, okay, apparently this isn't valid Haskell, so let's call this unit. Well, we can't put void in here. Okay, let's do it this way, I suppose. So if you want to think about cardinality of these things, you can by basically doing some like syntactical math. So we'll say the cardinality of void is 0. Cardinality. So given a data constructor, the amount of inhabitants inhabitants. Inhabitants. There's going to be a lot of terminology with this one, so which may be good for some people, and it's going to annoy some other people. So actually, somebody told me about a documentation format in Haskell, but I already forget what it was called. Maybe I should put like actual docs in here, but that's okay. Inhabitants. Do this. Data construct. Syntax. Inhabitants. Is that readable? So void doesn't have any inhabitants. Unit has one inhabitant, which is void, and then bool has 2 inhabitants, true and false. Okay, so this is cardinality. Any 2 types that have the same cardinality will always be isomorphic. So we've come across another thing, isomorphic. Hopefully this is useful the way I'm typing this. If it's not, we can think of a different way to do it. Like I could put this in a LaTeX document or something, but this should be fine, I hope. So isomorphic. Any 2 the same cardinality are isomorphic. That's a useful term. So to be isomorphic, you need to be able to define the following functions. So 2 is S to T, and from is T to S. Okay, so if you can define these two functions for a set of data constructors that have the same cardinality, they're isomorphic. Well, no, that's not correct. It's if they have the same cardinality, to and from can be defined. And there's some laws here, because of course there are. To.from equals id. From.to equals id. Okay? Are isomorphic. And we can define the following functions. So one thing I have to ask, by the way, I forgot about this. I need to ask Sandy if I can just put this code online for anyone to look at. I don't. So with Haskell programming for first principles, I was asked not to, but maybe that's not the case here. We sometimes write an isomorphism type, between types S and T as ST. Hang on. So we'll put this up here. Syntax. S. I don't know how to make that symbol in LaTeX. It's something like sim. So, oh wait, don't I have one of these open? Yes. So if you guys have any questions for me, just go ahead and ask. I think this first chapter is going to be a little slow. Well, not slow, but I've already done this before, so just let me know. LaTeX, math, symbols. So I write LaTeX a lot, but I just don't remember what this particular symbol is called. So give me a second. It's probably sim equal. That was going to be my guess. Looks like congruent. So this is what we need. That looks terrible in this font. Kong T. So just for reference, Kong T is like that on top of that, right? Maybe I should just write. I don't know. How do people feel about LaTeX math? Should I actually write this in LaTeX? I don't think I want to. I feel like it's gonna be a lot of work. If anyone has any opinions about how they want this written, let me know. So, anyway, I'm gonna use this for now. So, any two data structures with the same cardinality are isomorphic. We can find the following functions. Yeah, this is fine. We can define the to and from functions. Like so. Okay, so, and then we have some laws. Let's put these up here. Laws. And then we'll kind of space these out a little bit. Okay. Isomorphisms. Wonderful. So let's do an example. So if we had data, spin, up, down, one can write two, but let's keep this undefined. And then let's put this down here. Okay. So, bool and spin are isomorphic. We can write 2 in the following ways. So, let's call it 2 spin, which will be bool 2 spin, 2 spin true. I probably need to put some primes here, don't I? Oops. Up. Down. Right, so that's one option. You can also write the, well, I don't need to. You can either write these 2 things. I'm sorry. Let me put some primes here because I don't want to screw with the data constructor bool that comes with Haskell. So I'm trying to, oh, and I need to put some primes here or something. Okay, so these are 2 equivalent ways to write the isomorphism between bool and spin, depending on how you want to define them. And you can also, right, these have to have pairs. So from spin, let me write the pairs. Sorry. Up equals true. From spin, false equals, down equals false. True. Okay. Oh, except I have this wrong. Spin to bool. Okay, type check. So there are 2 different ways to write the to and from functions for this, but they have to be the same. So like you can't use this to spin with this from spin because it's not equivalent to id. I suppose we could write actual quick checks for this, couldn't we? Do we want to? Probably. I feel like I want to because I want to practice with all of these things. So let's actually write the quick check laws for this. I suppose we don't have to write quick check. We can just write let's do that. Why is this complaining? One problem. Oh, this doesn't exist anymore. Okay, that's fixed. And then we're gonna do an identity check, I suppose. So what do we need here? We need, I keep opening up a new tab, but I already have one open. I've already done something like this, so let's just grab my other example. github.com/parser. So I'm working on some of these checks. Where is it? Rational. Right, we can just put this in. We can just put this in a test, which is useful. We don't have to put it here. Print hello. So we'll put it actually in our test file. Then we need hspec. Whoa. Oh, no. Hey, Oren. How's it going? How's your day? We need to get this as well. So this is going to go in package YAML here. hspec. We made some modifications to the bottom of the screen, Oren, and then also now we're starting this actual chapter. So we've only talked about cardinality and isomorphisms, but what we're going to do is we're going to test our isomorphisms that these two are okay, but you can't pair the cases where these laws aren't true. That's what we're going to do, because I want to keep practicing other things. So, and also there's not a ton in this first chapter, so I'm going to try and milk it for practice. Hopefully that doesn't piss anyone off. It probably will, but I'll live with that if I have to. Okay, and then we should be able to restart GHCI, and this should be okay. What is this complaining about now? I'm not sure what it's complaining about, so let's just write our hspec here. Okay, so hspec do describe. We also need to import lib. Ugh, I don't understand why that doesn't work sometimes. How is it on the phone? I've not been able to watch it on my phone. I feel like it's too annoying for me, but I usually watch it from a computer, so lexical error at. Huh? What does that even mean? Is to spin from spin isomorphic. We'll come back to that error. I don't understand what that means. So do, it, do, and then the thing. To dot from is equal to id. Do. So we'll have to spin takes a bool, so true. True. From spin. Right, so if you this is spin, I don't know, to prime from prime. and then this one loses the prime. This one. Wait, oh, I did the same thing twice. Prime. Prime. Oh, with the reverse function. Okay, let me look at that. I was thinking about doing QuickCheck, but so QuickCheck properties, I guess. Haskell, probably enough. Property. So what do we want to look for? Probably like functor. No. I'm just looking for docs. Trying to be better about looking for docs first. So essentially we're gonna need we already probably have an arbitrary function for bool. We just need one. Yeah, but how do I actually do it with QuickCheck? Don't I need a property to check? I just, how do I make my own property, I guess? Maybe there's something in here. Something like this, right? Okay, well, yeah, I think we can do this. So given, then we, okay, I think I can do this. I can do this. Yeah, we have to write all of this, so let's not do that. Let's do it with QuickCheck. It's just in test QuickCheck, I believe. What is this lexical error thing? There's like a weird character in here, I think. I don't know what's going on. Okay, anyway, it's moved now. So there was like I must have copied in a weird character. Let's come back to this. Okay, in here, we're gonna change this to QuickCheck. And then we probably need to compile QuickCheck, so let's do that and then come back to this. Isn't that what it's... Oh, I need to... It's not QuickCheck like that, it's QuickCheck. There we go. Okay, so property spin. I gotta look at this again, but that's basically what we're doing. Okay. Spin iso equals. It's gonna take a spin, do something. I forget what the type is. We'll figure it out. with actual type. But I don't need to put this in parentheses, do I? I probably do, don't? Yeah. Okay. So then we need an eq instance for our spin type. Eq spin where I think it's just this, right? So up oh wait, I'm dumb. I'm sure it can figure out how to do this. I don't need to do anything. So this is one property, and then there's also a spin prime ice, which takes our primes, right? I suppose technically we don't need this id over here, but we can leave it there. Our other properties are let's call it not iso, and then just remove some primes from here, and then change these to not. Yes? Oh, I guess it's both the reverse, like you said, too, or the flips. But we got to do that with bools. This would be from spin to spin. This might be overkill, but you know what? I'm actually okay with it because from spin to spin. It's good to get in the habit of writing tests. I don't write enough tests in my life. So let's go overboard on tests so we get in the habit of doing it. And you know what? It's probably really boring to watch, so I apologize, but these are technically all the properties, right? And they should all be true. Or they should all hold. Now the question is, I probably do need a an arbitrary instance. So let's make that instance arbitrary spin where arbitrary I want to say it's like one of I just forget what it's called. What the actual. Choose. Okay, now we have an arbitrary type, and then we can just do our quick checks. Do quick check. Prop. Spin ISO. Bool ISO. Spin ISO prime. Bool ISO prime. This one. Okay. The other thing we probably want to do. Oh, right. These just produce bools. Create type signatures because I like doing that as well. I forgot that these just create Boolean values. They don't do anything else. I suppose this is what I was going to do with HUnit, but or HSpec, but maybe this is better. Prime and bool, not ISO prime. Okay, any red bars? No. So let's try and test this. Stack test. Random. Okay. It's not. I thought it was choose. Where is this from? I remember this frequency function. I suppose we can just use elements. Yeah, I think one of is the function I was using before, not choose. So let's try this. Oops. All right, let's go fix some errors. Okay. Oh, did I? Maybe I just don't have the right type signatures. I probably did that. So these ones are actually bool bool. So if from spin to spin is bool, to spin is bool. That's sort of the nice thing about leaving them off and then, you know, adding them later, you make that mistake, but that's okay. So there we go. It probably doesn't need to run 100 times. I don't exactly remember how to make it only do it a few times, but anyway, so there is a test that this set of functions is isomorphic with each other, or sorry, spin and bool are isomorphic using these functions, and these two functions are also isomorphic. However, you can't mix and match these. So if you use to spin and from spin prime, or from spin and to spin prime, those are not isomorphic with each other. Okay, cool. So we did isomorphism, and we actually tested it. And then it makes a point that, like, it doesn't matter which set of to and from functions that you pick for your, like, what's isomorphic. It's just what makes the most sense. So I suppose that, I don't know, spin up and true makes more sense to me, maybe. But, you know, up and true might mean something else to someone. Might mean something else to someone else. So they might prefer these prime functions instead of the main ones. So it doesn't matter which ones you pick as long as they obey the isomorphism properties, which are testable via QuickCheck, actually. Okay, neat. What's next? So we have more cardinality stuff. So let's start some more here. So for some types, the cardinality is the sum of the inhabitants' cardinality. So example, type oh, but this is usually defined the other way, right? Not that it really matters here. Cardinality is A plus B. Okay, this might be trivial to some people, but bool bool. Not trivial to me, so we'll skip the step where we drop the okay. Well, I suppose we can just, we don't really need this here. Or we can do it this way. How's that? I don't know. That's probably a little better, I suppose. So another example, maybe bool equals the cardinality of nothing. Oh, let's do it this way. The cardinality of nothing and the cardinality of bool three. So by definition, maybe and either are not isomorphic to one another because their cardinalities are different. Well, I suppose maybe bool and either prime bool are not isomorphic to each other, because if you put a nothing in here, then they would be the same. So you could define your to and from function. So let's write that. So either prime bool is not isomorphic with maybe prime bool. However, either prime, wait, you can't have nothing. Void, no, it needs to be 1. So I think I called it unit. Unit bool is isomorphic with maybe prime bool. Does that make sense? By the way, unit I defined as just void, but it has one occupant, which is void. Okay. A product type types. Sorry, couldn't type there. The cardinality is the product of the inhabitants' cardinality. Example. I'll just use their example. There's probably a simpler example. Should I simplify? I suppose it's not necessary. A equals fraction. Actually, we can just do this. Oh, apparently not. Mixed bit, the word 8. Why is H format failing? We're gonna have to look into that a little bit. a numerator is a, a denominator is a, apparently. So the cardinality of mixed fraction is mixed bit times, well, it's really not mixed bit, it's just word 8. Numerator, denominator. This is failing for some reason, it seems, but I don't see any squiggly lines, because otherwise I think, unless I'm, let's see, HFM, do I not have that extension? I seem to have. I'm not sure why H format isn't working. Maybe we just use a different extension? If it's not working, I'll try something else. I know of stylish Haskell. We'll use stylish Haskell. It doesn't matter to me. Oh, now there's an error somewhere. One problem in this file. Where? Oh, data. And word 8. I don't know where word 8 comes from, but it's probably data.bits. Oh. Does anyone know where word 8 comes from? Google will know. Google knows all. Word 8. Data word. Not bits. Word. And really we only need word 8 from here. Okay. Apparently the cardinality of word 8 is 256. So it would just be, oh, except I screwed this up too. A 256 times A times A. So if we did mixed fraction, well, we wouldn't do mixed fraction bool, but let's do it anyway as an example. Just because I want to just fill in some math. It doesn't make sense, but let's do it anyway. 512, 1024. Is that right? I think that's right. I swear I can do math. Okay. Oh, this one was confusing before. Let's see if I can. So apparently you can prove that x times 1 equals a So prove by showing an isomorphism between I remember reading this before and being a little confused, but I think it's just A. And then so this must mean that a tuple is a product type. Yes. So equals A times B. The cardinality of unit is 1. Therefore, the cardinality of A unit equals the cardinality of A times 1. So it's like an identity function. Cool. Okay. This seems a little off, like confusing to me. Does maybe somebody else this isn't confusing to? So because there's an isomorphism that exists you can say that A times 1 equals 1? Oh, right. Because this is equal to the cardinality of A. So any A here is this can be the same A here. Right? Is that what this means? So given A, this is true. So if you can show isomorphism between this and A itself, then this is true. Therefore, therefore these are equal. Maybe I'm thinking about this correctly. Let's put that on the next line. Something like this. Wait, no. Oh, I have this wrong. That's why. I was like, this looks wrong. I think this is right, logically, but it's a little weird. It's a little weird for me anyway. So void, okay, so it says, likewise, void acts as a monoidal unit for some types, right? Monoidal means combined with identity is itself, I guess. Monoidal identity. Oh, I see. I get it. So, let me show this. I see what I see what that means. So instance monoid. It's mempty. That's what it is. Unit. So for a sum type, mempty is, or unit is 1, or I'm sorry, for a product type, mempty is 1. For a sum type, mempty is 0. So, or in other words, void or something like unit. Okay, I'm okay with that. That makes sense to me. Function types also have an encoding as statements about cardinality. They correspond to exponentialization. Okay. So if you have a function a to b, so function, I gotta remember how I organize this. Yeah. The cardinality is computed as, I always get this backwards, by the way, b a times, so as the right operand, the result type to the input type's power. The result cardinality to the input cardinality power. Hopefully that's not off the screen. So example, b is basically b times b times b dot dot dot, which is equal to I don't know how to write this. It's like a product of b and a. So what if we write sigma rho I think it's pi, 0 to a of b sub I might have to check that in a LaTeX. I feel like I've seen one of these recently, or I've used one recently, if I can find it. Code cop. Oh, okay, I can just use prod. That's useful. Let's change that. So let's make sure this looks right. Let's ignore the arrow problem. I equals 0 to the cardinality of A, B sub I, B. And we'll also ignore this, but I just wanted to get at least it close. This might be completely unreadable, so sorry. Let's put this back over here in case we need. Bye. Might need that later. So prod A. Okay. Sorry if that's not something anyone's familiar with, but that's what we got. Okay, so now we have an exercise. So that's fun, something to do. What the hell? Determine the cardinality of either bool, maybe bool, to bool. All right, so first things first, we probably have to deal with the exponentiation. So it's b to the a. So bool to the, we'll put this in parentheses, this whole thing. So an either is a sum type. So we have bool plus parenthesis a product type. So bool. Do those look crooked? My eyes make them look crooked. Times. And then we have a maybe, which is a sum type. So 1 plus bool. It's like nothing plus bool. Right? Okay, so 2 parenthesis 2 plus parenthesis 2 times parenthesis 1 plus 2. Uh, 6 8. What's 2 to the 8th? I honestly don't know. 256. That's useful. 256. Okay. This book, which is really nice, actually has answers in it. So thank you for that. If you're actually watching, I appreciate that. I can see what you do, but I think that this is right. I vaguely remember doing this before. Yep, that's right. So, assuming I didn't goof up any math, or like the order and just accidentally got 2 to the 8th, I think we're okay. So there's our first exercise in the book. Done. Look at us. Okay, so they make a point that's kind of interesting. Subtraction, we don't see subtraction or division or any other mathematical operations. So, maybe these could be applied to types, but apparently they're very hard, if not impossible, to express in Haskell. So if you're wondering, let's see, subtraction corresponds to types with particular values removed. So like, I guess subsets? Well, division of a type makes some of its values equal, in the sense of being defined equally rather than having an eq instance which equates them. That's kind of weird. Excuse me. In fact, even the notion of differentiation in calculus has meaning in the domain of types. Apparently, Connor McBride has a paper called "The Derivative of a Regular Type is its Type of One Whole Contexts." I don't know what that means, but okay. Okay, so being able to manipulate the algebra behind types is a mighty superpower. Let's prove it. So let's make a tic-tac-toe board. A bad one. Tic-tac-toe. A equals tic-tac-toe. Oh, you know what? I forgot something. Hang on. Top left. A. Top center. A. So one thing I wanted to do is try stylish. Okay, stylish Haskell worked. I don't know why H format was giving me grief before. Okay, and then top right. And then center left. Center right. Bottom left. Center right. Okay, so this thing works, right? One can create this thing, but actually making this kind of stuff is going to be really annoying. So if you wanted to do like empty board, tic-tac-toe, maybe A, you would have to write this. Tic-tac-toe, nothing. 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 Missed one, right? So this is pretty difficult. If not, I mean, it's just annoying, right? I mean, I did it wrong the first time. So we're going to use the power of algebra to figure this out. So if you wanted to like figure out if someone won, that would be much more complicated. So if we wanted to figure out tic-tac-toe A, it would be A to the 9, right? Which is exactly equal to A to the 3 times 3. So what you could have, I think is where they're going, is you could have a function that returns an A that has 3 that has 6 inhabitants? Is that right? So isomorphic to right. So it's isomorphic to something like this. So if you had a product type of something that contained three things and 3 things to A, so you could make that by saying 3 to 3 I don't know why we're going to need to drive all this stuff, but maybe they're going to show some code. Enum bounded. You could write data tic-tac-toe prime of A. Tic-tac-toe prime board 3 A. Okay. And then, oh, that's why we do that. So then you could write empty board prime, which is tic-tac-toe prime, maybe A, is a 3. I'm gonna have to think about this for a second. Const nothing. Okay. Takes a maybe A and a 3 and throws away the 3, so we just get maybe A, and then we do the same thing here. Isovector, hey, what's going on? I don't think I recognize your name, so you might be new. What's going on? How's your day? We are learning about isomorphisms and cardinality. It's pretty fun. But as Oren will, oh, wonderful. Hey, you're teaching me stuff then. I like your book so far. You have answers to the questions, which is really helpful. I'm glad to see you're here. I emailed Sandy so that to make sure that he was okay with me using this book on stream. Oh, since you're here, can I ask you a question? Can I post this code? Oh, no, that's fine. I like being distracted. Distraction is good sometimes. Can I put this code on GitHub for everyone to see, or would you rather me keep it private? I can do either. I don't mind. Yeah, I thought so, but I was gonna ask you anyway, just to be sure. So that's for everybody else. This will be online and free, as the book is as well. But you should support Sandy if you can, and go to that book. There you go. I think that's the correct place that you're sending people. Correct? Not there's like another publisher that's like this. Lulu? Is that the right name? I think it's Lulu. But anyway. Good. Wonderful. So I'll keep going. Well, this is a hard copy. I got this from LeanPub. Do I have a choice of a soft cover maybe that I just wasn't paying attention to? Anyway, you can get them for both. Oh, LeanPub has the by hard copy you mean physical copy. This also has a ebook. Oh, maybe I bought it. Maybe I bought it from Lulu then. I don't remember how I got this. I got it somehow. Anyway, we'll send people here. No, that's fine. Don't apologize. I'm glad you're here. That's actually really cool. I want to get good at Haskell. I'm gonna try. So let's encode. I actually used Haskell at work today. I'm really proud of myself. It wasn't anything crazy. It was just a pretty boring, like, run a command, parse the output, use that to run some more commands, kind of shell script. But I used Shelly, which I had never used, and also megaparsec, which I've never used. So I thought that was cool. So let's give some examples here. Yeah. So okay, so Curry-Howard Isomorphism. Every statement in logic is equivalent to some computer program and vice versa. All right. So we have, like, in algebra, I'm going to skip the logic part only because I don't know anything about, like, logic. I know that, like, these mean things, but we'll say we'll just use the computer sciencey stuff because it's easier for me. A plus B is like either AB, some types, product types are like AB, B to the A is like AB. I don't know why, but when I first did this, I had a really hard time remembering that B is the return type, but I seem to be okay with it right now for whatever reason. A equals B is isomorphism, and 0 void 1 unit as such. Okay, so this is our sort of, here, let's do this. I don't know if that makes it more readable or less readable, but looks like something to me. Okay. I like this. Curry-Howard isomorphism is a profound insight about our universe. I would agree with that. That's interesting. What's better is that often even boring mathematical theorems are interesting when expressed as types. That's a cool thing. Okay, let's do this. So, example. A to the first power equals A. In Curry-Howard, represents a function of unit to A, or sorry, an isomorphism. So let's do it this way. In Curry-Howard represents an isomorphism between and A. Let's put these in backticks just to be clear here. That's okay. All right. I gotta read this again. I like this statement as well. This theorem shows that there is no distinction between having a value and having a pure program that computes a value. That's cool. I feel like there's a lot of cool wisdom in here like that. I've read more than just this chapter thus far. Like I got to chapter 4 before I kind of stopped because I was focusing on the Haskell programming from first principles book and I just didn't have time. But you know, there's a lot of really cool little things like that in this book that I like quite a bit. It makes it feel, you know, it really helps you tie in like Haskell from one side and math from the other and where they intersect, it seems. And, you know, that's a really, for me, that's a really important space. Okay, anyway, we got another exercise. I think I had trouble with this one before. So, prove, well, using Curry-Howard dash prove A to B to C is isomorphic with A to B times C. We don't use X, so that should be okay. All right. That yeah. A. See if I got that right. BCA. BCA. These look like curry and uncurry now, but I think when I looked at this before, they did not look like curry and uncurry because I didn't know what they were. I don't remember which one is which, so we'll have to think about that. I want to make sure I got both these right, though. No, I don't. I read this. I wrote half of one function and half of the other. BCA, BCA, like so, and BCA, BCA. Okay. And let's put backticks around here. Now that I'm thinking about your Twitch name, by the way, I'm pretty sure that's the same name on GitHub, right? I was just thinking about that. Same one. I don't know what made me think of that, but something did. Okay, so let's not call it A. Let's just call it fun. Oh, wrong tick. A. We have f again, and yz equals f c. Okay, so the question is, which one is which? One of these, I think, is curry, and one of them is flip curry or something. Or, I don't remember. Let's go look them up, because... Oh, I guess we can just REPL them. Type curry. Stick this here. Stick that there. Get rid of this. Okay. So B. Yeah. So this is curry. And then I guess that's uncurry. B. Yep. I don't look at these functions enough. But anyway, yeah, so that bigger, there we go. We might need this later, but probably not. Probably make it smaller as well. Okay. So these are our to and from functions. Is that correct? Let's see here. I'm trying to remember what we just proved. Have we proved anything? Or do I need to write some more algebra first? I think Curry-Howard prove a to the b to the c is quick with to the times c. BC. Okay, so this is represented by this series of functions. Oh, right. Yeah. Okay. So these are to and froms. Yes. These are to and froms. Sorry. It wasn't easy to read for me at first, but I see it now. So this is let me write it in a different way. Yeah. I see it now. It took me a second. So let me write it a slightly different way. So B, C to A is A to the B times C. I'm gonna write sim to mean in Curry-Howard. Curry-Howardified. I don't know what the right term is there. A to the B to the C is A, B. No. A. Yes. So these are to from functions. So we have to prove that. Do we really need to apply these to prove this, or do we not? Is this enough? Or do I actually have to run some sort of test to make sure it's correct? I'm not sure. I'm gonna read what you said. Because we can write a function of a to and from function, these things are isomorphic. Convince yourself that compose one after the other, you get id in both directions. Yeah, so fun.fun prime is equal to id. And vice versa. Let's name these something better. What's a better name? I mean, uncurry and curry, I suppose, is a better name, but that's fine. That. The question is, have I sufficiently proved that to myself? Maybe that's the question. Or should I do a test? I mean, we can just do a test. I feel like there was something else I wanted to do a test on. Maybe not. Let's just make a test. So we need some types, I guess. So what do we want to do? This me. um we need a BCA and a BC. And for now, we'll comment all this out. We'll come back to that here in a second. Okay, so we can just pick like multiplication and be done with it, I suppose. And then we want to prove the property that, I don't know, we'll call it just Curry ISO. This is going to take like an integer and make a bool. Can't take one. Did what? Time? Takes two integers. Why? Right. Why is it not? It's probably because the composition of these is way more complicated than I'm thinking. Yeah. Can it do that? But I see what you're saying. Right, because it's not, I'm picking an actual picking an actual f is not what I want to do. Right. And these things, there's going to be something I have to do here though, right? I'm going to have to make a co-arbitrary instance or something. So that function needs to be able to derive co-arbitrary. Is that right? I don't know how to write that. Each one needs to be co-arbitrary. I think that's right. If they have concrete types, that could be true. And we should probably pick concrete types to make it easier. Let's just do there's more functions that one can choose when picking integers, I suppose. Well, there's let's be clear because we know the answer to this. There's integer, so that many potential functions to build, right? Result type, yeah, or this. Fun. Look at us using this correctly, I guess. I think. All right, let's try that. But I think you're right. I think you get them for free if they're concrete, assuming the integer derives co-arbitrary. or there's an instance of co-arbitrary for integer. I think I'm saying that incorrectly. We'll see if it compiles. No, it doesn't. Oh, it's not F1 anymore. It's whatever I called them over here. Fun and fun prime. Oh, I have the other one. This one is fun prime fun. Right, maybe not. Yes. We can't equate these two things. How do we equate functions? The types are right, but I don't know how to do this. Hey, Lumi, what's going on? Oh, so we just need to apply them to something. Okay, right. So this produces, yeah, good call. Yeah, but we're quick checking, so we're only gonna do 100 of them, right? So it should be fine. So we'll just give it, well, can't I do, I think I can do this as well. Yeah, but technically this would never, we'd never be able to do this correctly, I suppose. But I think we can do this, right? The issue here. Okay. No. How do I make this work? I feel like I did this before. Oh, yes. Yeah. See? By the way, Lumi, hey, how's it going? How's your day? And I also saw Orin, who must have come back after a little bit. We are doing stuff. We're trying to test basically this property that these two functions are isomorphic. And I didn't, yeah, it didn't work so good. That's unfortunate. I think the phone is hard to get. Like, it's just small. And then if you have the, like, the screen is small, generally speaking, obviously. And, you know, if your connection is at all spotty, then you have problems. Right. It thinks it's point free. But I should probably make this specifically, although I suppose it doesn't matter, but we'll do it this way. Thank you for the. Well, is flexible instances in this book? I know you do a lot of the language extensions. I don't remember seeing it offhand. Lumi, I don't know how you do that. That's okay. Okay. The language extensions is definitely something where I feel like the HPFFP book could benefit a little bit. That's abnormal for you, right, Lumi? You usually do the opposite thing, if I remember correctly. Also, I think, Lumi, it was you that we were talking about with. We were talking about doing like an actual project. And I think I've decided that I would like to do an actual project, so I want to tell you about it while you're here. I think what I want to do is build a bus application, like an application where you see bus times, because in Pittsburgh, all the bus apps are a little obnoxious in their own little ways. And so I was talking with somebody about this, and the idea would be, I know at the end of the day, sometime between 5 and 5:30, I want to take bus X or Y to, going this way. And all I want the app to be able to do is allow me to put that kind of information in, and then give me back like you should leave in or at 5:15 because your bus is super late, something like that. So that's what we were thinking about. And I sort of want to learn how to make a REST interface, because I've never done that before and I don't really know exactly what it means. So I was thinking about trying to make like a Haskell REST API that goes and queries the data and somehow caches it and something like this. And then like a front end app that just communicates with the API to give the user information. So I think that's what we're gonna do. Now I don't know how we're gonna do that yet. So I'm still thinking about that, but that's an idea. Okay, let me read Sandy's post here. By default. Yeah, I was thinking with Servant just because I want to learn Servant, and it seems like it's the new, not, I don't know how new it is, but it seems like it's the cool thing that people are using right now. All instances in Haskell must be in the form type constructor. Okay, so the flexible instances allows me to nest type constructors, because this is a type constructor, the arrow. Okay, that's useful. So yes, I'm thinking Servant for that. Okay, let's see if this works. Yeah, so that was another thing I was thinking about, potentially asking somebody else. Let me try and quick test this. I was thinking about asking somebody else to help me with the front end, because I don't really know anything about that. But I think it would be cool to do it. And a friend of mine is using PureScript to do some front end work. So I was thinking maybe I would try and do the front end in PureScript and then the back end in Haskell, and that might be kind of a neat app. Yeah, but it's got to be. Well, I don't know all the details of GHCGAS either, but I want to be able to put it on a phone. So as long as I can put it on a phone, I'll be happy. Anyway, so I mean, yes, we've only done 100 tests, but those 100 tests tell me that these two things are isomorphic with each other. I should probably do the other one, right? I probably have these backwards, but I'm not terribly concerned about that. So this one's going to be this way, and then we got to do this. Oh. I have to tuple these up, I guess. B. Okay. Yeah, I mean, we can look at different front end stuff later. I think the back end stuff's going to take me a long time because I just don't know how to do it. So I think we need to do some type checking in the terminal here because so type fun prime. Oh, probably. Oh, yes, I really did. Okay, there we go. Thank you. Yeah, very silly type signature. Okay, that's funny. Oh, we got this same. And okay. So seems to have worked. So we've proved that these two functions are isomorphic, and therefore these two things are isomorphic. Very cool. I suppose again we probably didn't do enough. We may have not done enough in actual tests. Like in theory, there are infinite ways to check those functions, but hopefully we've done some of the hard ones. Okay, so now we're gonna do the same thing for a to the b times a to the c Oh, I wrote X, I meant C here. Yes. Yeah. Yeah, these two things are equal. I said isomorphic, but I guess equal is probably equivalent in this case. Or isomorphic is equal, right? In Curry-Howard. Yeah. But that's, yeah, like making me think about that is important. Okay, so we have a product type of two functions. So we have to have a product of B. Sorry. The result type, it's B to A. I'm confusing that again. And C to A. And this is sum type, which is either BC I think. B plus C to A and B to A, C to A. Okay, so we need to prove an isomorphism. So, yeah, thanks for dropping by, Sandy. I'm having a good time thus far. This is very enjoyable, so I'm glad to do it. We're gonna start projects. I don't know when. I still haven't figured that out, but we're gonna be doing projects some nights and theory some nights. So that's the plan. But I don't know when yet. So, but thank you for being here. All right. So B to A. Oh, I love doing this. This is I'm learning so much. It's like exactly what I want to do in life, generally speaking, is theory. So either B, C to A. Let's just explicitly call one of them to and one of them from. B, C to A to B to A, C to A. Yeah, new maid, sorry, it starts at 7:30. Yeah. I don't know if you have a time conflict like Lumi does, but if I remember correctly, you were able to watch on time that one time. So unfortunately, yes. But we're not done. Oh, I guess we are done. Holy crap! It's 9:40. Yeah. So isovector, who is, I don't know if when you just come in here if you can see the chat, but isovector is actually the author of this book. So and he followed, so that's really cool. And then there is someone named Labossel. I don't know if they're still watching. Okay, yeah. So again, yeah, isovector 1 is the same. He's the author of the book, and so that's really cool that he's hanging out. He sounded excited about what we're doing, and he's got a lot of really useful information. So that's cool. Yeah, it's isovector 1. I don't know if that was the same person you watched. But this is the types book. Yep. So we're learning about Curry-Howard, and we're trying to do some theorem proofs. Or proofs? I guess they're proofs. Sort of. They're not the same as mathematical proofs, I suppose. They're Curry-Howard proofs. Okay, so we need to be able to write this function. So if we had an f and a g and a right, I suppose we can just do left first, of x, if we have a left, and yeah, I haven't done like a true mathematical proof in a long time, and there's like, I think that's a little different. So I'm going to call this specifically a Curry-Howard proof, just to say a Curry-Howard isomorphism proof, just to be, I don't know, I don't want to be wrong, basically. But this is going to be f of x this is going to be g of y. Here we don't need this, and we don't need this. I might be being over technical in that case, I'm not sure. So here we're gonna have like a left X, an A, or a right Y and an A. And we need to make a tuple. Something goes here. Um, hmm. So if we have a left, that's a B. So we can write oh, this is BAB. But they probably gotta go the other way. This is not right. So this is what I had a hard time with last time. I have a B and an A. I need to make functions out of those. I suppose we can look this up in Google and see if this is something. So we have like an A and a B, and we want to make a B to A. Let's flip these. B, A, B, A. I guess this is what we want. So we want it BA, so we have to do XA. that didn't look like the type there. I think I couldn't figure this out last time as well, or it took me a long time. Yeah, because this needs a function to apply. We don't have a function, so how do we make a function here? Wait, this isn't correct. That's why. What am I doing here? This is a product. It's because I'm dumb, that's the problem. If I wasn't dumb, then I wouldn't have this problem. So that's that one, and then this one is no, product type. I was right the first time. Product type. I guess I don't understand how you do this if it's not just const A, const A. In both cases, right? How else does this type check? It can't, right? I mean, you can't. I don't think there's any other way to write that function. If someone can prove me wrong, I would appreciate it. Okay. Well, anyway, we can try and prove it here. Prop xe2 is going to take one of these functions. Excuse me. The heck? Okay, let's do it this way. So it's gonna have to take f and Yeah, this has been really wild, actually. We're learning a lot about um, isomorphisms and cardinality, I think. It's pretty tricky, though. Or at least I think it's tricky. It's very interesting, though. I'm having a lot of fun doing this. Okay, so we have to do something very similar here. So we're going to compose to and from. So this is going to be like... Uh, well, this is problematic. If I can't compose to and from, I'm doing something wrong. So the exponent goes first. That's the exponent goes first. A product is this. Um, B plus C is either, and the exponent goes first. But I can't compose these two things. It's probably because they're. I probably need to give a definition for this. So it knows the right thing. Because the B's are the same in this case. And I don't think it knows that. Maybe there's a trick to make it... Right, you can see it when I do this. Well, when I do this, you'll see these B1s. But it's not B1, it's B. So we'll copy this in. Oh, I can't do that. Okay, fine. So we'll copy this. Okay, let's make sure I got this right. B to A, C to A. Either B, C, A. Either B, C. either BC, BA to either BC, either BCA. Long. So I think good. By the way, this is a good catch because that actually changes the way this function is written, right? Because this is supposed to be like this, I think. I'm not given an explicit A, I'm given a function. I gotta think about it that way. So if I want to get a B to an A, I need I don't know what I'm doing. But yeah, I tried that, but then I don't understand how to write this function. That's why I feel like it's wrong. So if I pattern match both let's say I do that, right? Left X, and M or something. M, right? Yeah, I feel like I need to actually pattern match on like 1F. M in that case was just some A. Or maybe this is wrong. Yeah, M is, in this case, is just an A. This won't type check because of these parentheses, but if I get rid of them, then that's an A. But I don't think that that's correct. I think that the real type signature is supposed to be like this. I'm supposed to deal with like a single f here. But I don't know how to get this B to A, C to A out. Because if I was to like, no, F mapping is composition. Can I just do what are the types of these? I'm missing something, I think, so I don't know what I'm doing. That's really what's going on here. I knew it was something like this. But I think this is it. So if you're given this, you need to first get B. Okay, let me see this again. Let me read this again. This might say, if you give a function that parse the ether and return A, I can transform it to a tuple of two possibilities. Yes. Yes. But I think this is how you write this. And the way we'll know is if I can get rid of this and they compose. That's the key there. The types work this way. Okay, now we're getting somewhere. This is tricky though. So what's the type of this? I can't do that. Either BCA, BACA. So we need to make either BCA to BCA, right? Okay, and then we need to replace all of these with a concrete type. And then we need to apply these. So we're gonna apply them to an F and an either. So we need okay. Oh, yeah, so I need explicit types here. So what's this F supposed to be? this produces an integer, so the integer goes away. Because we're going to compare the two integers. So we're going to get an F and an A. Got it. That's tricky. Okay, so again, the composition of these two functions gives you, I can't ignore this. Imagine if this is integer. So what we want to do is say the left side applied to an integer, applied to an either integer returns an integer. So the left side returns an integer and the right side returns an integer, and those integers should be equal. Does that make sense? And if they are equal, then these two things are isomorphic. And if they're isomorphic, they're equal. Wild. So I think we need an instance of show for either integer, integer, integer. This is pretty wild, right? Where? Okay. And then we can write the other one. I want to write both of them. So let's put these down here. QuickCheck prop. Is everyone following at least what I'm trying to accomplish? Maybe not exactly the types because this is pretty complicated in here, but okay. So from 2, we'll do this again. Oh, wrong 2. 2. We'll look at the type. So this gets this one's going to be harder, right? I guess not. We just need to apply to 2 things because we need a B and a C. We're getting a B and a C. And we're round tripping it. Okay. So this is so we need this, I think. So we're gonna get an we're gonna get this, but we're gonna apply it out. I think this goes away. I think we're gonna get FAB. And we're gonna say where G H equals F. We're going to say G A Holy crap. All right. I mean, it looks right, but I didn't think I'd get it right on the first try. Who knows if it's going to be right? I guess. It looks right, like, thinking about it, because, right, this F is this, right? So I need to first compose the functions applied to F to create a new G and H, right? Once I have my G and H, I can apply them to A and B, and then compare that they're equal to the originals. That's what I'm doing. If it doesn't make sense, I can go over it a little more carefully. But maybe like, we could write it a little more. We could probably write like A prime equals first id F A and B prime is second id F A, and then that gets rid of, oop, it gets a little cleaner looking up here anyway. I'm lisping today. All right, so how do we get rid of the parentheses? Do I need them? Yeah, I think this looks better now. But I can't get rid of these parentheses, right? Seemingly I can just get rid of them. There must be something about the what's the term for that? Precedence that allows me to just get rid of them. Yeah. So it must be smart enough that this requires both the outside things to be evaluated. So I guess equal equal has higher precedence than ampersand ampersand. Right? I think that's the right way to that's the correct way. This is pretty cool. Obviously this one's a lot easier to write. Okay, moment of truth, and I'm calling it a day because I was hoping to get further than this. It was a short chapter, but everyone ready? Done. Oh, well, that would have been anticlimactic. Bum-ba-da-bum. Nope. Something's wrong with that code, but I don't know what, and I need to stop. I need to stop streaming. Or I can look at the answer. We gave this the old college try, but something's wrong about it. I can look up the answer real quick. Either this is right and this is wrong, or this is just wrong, which implies the other one's wrong. Are we okay with looking up the answer? I think that, I don't know. I'm doing it. Yep. Yes. So these functions are correct. The only thing he changed is he used an arrow here in between these two functions instead of a tuple, but it writes functionally the same. So something about our test is wrong. And if we look very carefully at this, it's the second one that's wrong. And the first one is correct. So if we just comment this, sorry, not that, the types work. If we just comment this out, it's actually okay the one way. But my guess is something about, nope. Something about this function is fundamentally incorrect. Hey Ryan, it's Barry, but you're very close, so I'll give you the benefit of the doubt. How's it going? We're streaming super late today, so I'm actually about to get off, but I'm generally doing well, and we've had a lot of fun today. Nervous? What are you nervous for? Hopefully nothing problematic. What if we just put parentheses back in here? I don't think it matters, but I'm genuinely curious. No. Yeah, I understand that feeling, but that's great to hear you got your A. And if you continue in CS, I mean, CS is a great field to be in, so you're probably going to be fine. But I understand the mind playing games with you, because yeah, you got to pass. Yep. You got to pass anything though, right? No matter what topic you choose, you still have to pass. So it's just, you got to find the thing that you love and then just do that. But I'll give you one suggestion, because I give this to every undergrad that I've ever encountered. Take as much math as you possibly can. Even if you think it's going to be hard, take it. It's very important that you are fluent in math. So yeah, calc is hard, but I'm telling you, you will greatly benefit from doing as much math as you possibly can. If you have it in you, I would even suggest trying to do like a math minor. I would suggest that to literally every undergrad in any field, because the only thing that will ever hold you back in life is your ability to do math. Just keep that in mind. But yeah, it's just practice, do your homework, you know, try hard, party a little but not too much, you know, that kind of stuff. Well, just a question, is Cubs like the Chicago Cubs? Before I go, but I really need to go. It's super late for me. Animal. Oh, okay, that's fair too. I like critters. I got two cats of my own that you could call them my cubs, if you will. Anyway, Ryan, if you want to come back and keep talking to me, I'm totally into it. I see you followed, so you'll see when we stream next. Thank you for that. And this is what we're going to be doing. So I think next time we got to figure out what's going on with this code, because something is wrong. Oh, wait a second. Shouldn't that be a B? That should have been a B. I think. Why am I not getting type fail from that? Yeah. Bug. We did it. Look at that. Although I don't understand why I wasn't getting a failure for A, because that would have been the wrong type. But anyway, we did it. Okay. So we've proved this isomorphism here. So we know that these things are equal because we've Curry-Howard them. How cool is that? And I did it without looking at the answer. Well, I looked at the answer to make sure I was right, I suppose. But there was a bug here, and that's the only thing. Oh, it worked because everything was an integer. That's why. It didn't matter whether it was A or B, so maybe integers are a terrible choice. Okay, seriously, I need to get off. It's super late. I gotta go to bed. So thanks for all the followers. We got 3 followers. I feel like we had a ton of viewers today, so that was super awesome. Just a reminder, this is the book we're working on. You can go get it yourself. I'm in chapter 1, and I'm already having a very fun time. This is a very strong theory book, though. So if you're not into theory, I wouldn't suggest this book as your starting book. There are better Haskell books to get started, and we can talk about those next time. So I'll see you on Thursday at 7:30, and we're probably going to be excited about this book the whole time and go way too long. So we're going to be coding a lot soon. So thanks for watching. I'll catch you all later.